Hello everyone, welcome to ACE Online and KPTCL lecture series. Our today's subject is a most beautiful subject, one of the core subject of electrical engineering, titled Power Electronics. Okay, and we are going to focus on AC to DC converters. So friends, myself, Professor Rajendra Garase, I have done M.Tech from Indian Institute of Science, Bangalore. I was the All India 7th ranker in the GATE examination and working as a faculty of Power Electronics at ACE Engineering Academy, Hyderabad. I am having a more than 10 years of teaching experience. So our today's topic is AC to DC converters. So before moving towards the today's topic, let us introduce a subject, power electronics. Okay. So first of all, we are going to discuss the introduction of the power electronics. In that, what is the definition of power electronics? What is the syllabus of the power electronics, as long as the KPTCL is considered the weightage for the power electronics in a KPTCL and the recommended books. Okay, so let us discuss one by one. Yeah, definition of power electronics. Yes, can anyone? What is the definition of power electronics? Come on. You can post your answers in the chat box. Definition of power electronics. As it is the combination of two terms. One is the power and second one is the electronics. So friends, power electronics is a technology that is used to control and convert large amount of electrical power with the help of electronics. Okay. So this is the technology in which we are interested in controlling and conversion of large amount of electrical power with the help of electronics, right? Means by using the electronic devices, by we are going to control and convert the large amount of electrical power. That is nothing but the power electronics. So friends, here the two terms are very important. One is control and second one is convert, right? So one is the control and second one is a conversion. Control and conversion, the meaning is, control means we are interested in controlling the output power, that is the load power. So your load power is should be variable one. And conversion means, yes, we are having the AC and the DC supply, or the AC and the DC powers, right? So conversion is nothing but either AC to DC or DC to AC, right? So controlling and conversion, these are the important things. But how we are controlling the large amount of electrical power? With the help of electronics, with the help of electronics. That is nothing but the electronic devices. That is nothing but the semiconductor devices. So friends, let us discuss the syllabus. As long as the PSUs are considered just like a KPTCL. Okay. So which topics are there in the syllabus? Let us discuss. So first chapter is introduction. Okay. Second chapter is the switching devices. In this chapter, we are going to discuss what are the different switches, what are the different semiconductor devices, those who are going to use as a switching devices in a power electronics or in a power electronic circuitry. Third chapter is the AC to DC converters, or it is also known as a rectifiers. Okay, input is a fixed AC, output is a DC. So it is a AC to DC conversion. It is also known as a rectifier. Fourth chapter is DC to DC converters. Input is a fixed DC, output is a variable DC. It is also known as a choppers. The next chapter is a DC to AC converters. Input is a DC, output is a variable AC. Variable AC means what? It gives the, this is the circuitry which gives the output in terms of variable voltage and variable frequency. It is also known as inverters. Next chapter is AC voltage regulators, that is AC to AC converters. Next, after that, cyclo converters. It is also known as a one stage frequency changer. And last chapter is the fundamentals of electric drives. Okay, only fundamentals, that is the introductory part of electrical drives we are having. So friends, these are the 8 chapters are there as long as power electronics syllabus is considered for any PSU, right? For any PSU. Now, out of these 8 chapters, definitely first chapter is only introduction part, okay? So important chapters are switching devices, AC to DC converters, DC to DC converters and DC to AC converters. These 4 chapters are very, very important. If you refer the previous year questions, you will find most of the questions based on these 4 chapters only, right? Next, so marks division, as long as PSUs like Genco, Transco, Discoms, KPTCL are considered, what is the tentative weightage of the power electronics? Yes, generally there will be around 8 to 10 questions of marks, 8 to 10 marks out of the 100. So friends, roughly the weightage is around 10% for the power electronics. So very, very important subject. This is one of the core subject. As I said, this is one of the core subject of electrical engineering. Okay. Next, recommended books. Definitely, whatever we are going to discuss in a live sessions as well as in a recorded videos, if you want to do apart from that, okay, classroom notes, I would like to suggest the 3 books. The first one is the Power Electronics by Dr. P.S. Bimra. Second book is Power Electronics by M.H. Rashid. And third one is the Power Electronics by Mohan and Robbins. Okay. So here, out of these 3, if you are preparing from a zero, I would like to suggest, please go for the book written by Dr. P.S. Bimra titled Power Electronics. Okay, very well written book, easily understandable book, okay, for average or below average student even. Okay, right. Now coming towards the today's chapter, AC to DC converters. It is also known as a rectifiers. Okay, so as this is the converter where the input is AC, output is a DC, right? So AC to DC converter or a rectifier, it gives the output either controlled DC or a uncontrolled DC. We'll discuss which circuitries gives the controlled DC, which circuitries gives the uncontrolled DC as well, right? So let us start with a general classification of rectifiers. So generally rectifiers are classified depending on 5 different factors. So let us discuss one by one. The first is based on the controllability of output voltage. Based on the controllability of the output voltage, right? There are 3 types. One is the uncontrolled, second one is the semi-converter, second one is the half controlled, or it is also known as a semi-converter, and third one is the fully controlled. Okay, third one is the fully controlled. So first one is the uncontrolled rectifier. Uncontrolled rectifier means it is the rectifier which uses only diodes. The rectifier which uses only diodes in the circuit, and the output voltage is uncontrolled, means for the given input voltage we will be getting only one waveform as an output voltage. So if you check the average value or the RMS value of the output voltage, we will be getting only one value, okay, at the output side. That's why it is known as the uncontrolled rectifier. Uncontrolled rectifier means where the output cannot be controllable. Output cannot be controllable means we cannot vary the output. Okay, we cannot vary the output. Now, this type of rectifiers consist of, yes, which switches? Only diodes are used, right? Controlled switches are not used in this type of rectifiers. Only diodes are used. Next, half controlled rectifiers. It is also known as a semi-converters. Half controlled rectifiers, or it is also known as a semi-converters. So half controlled rectifiers or semi-converters uses controlled switches as well as uncontrolled switches. Means it consists of controlled switches like a SCR and a diode. Combination of SCR and diodes are used in this type of circuitries. And this type of rectifiers, we can vary the output voltage of this type of rectifiers by varying the firing angle alpha. And how we can vary the output voltage? Output voltage can be varied from 0 to the positive maximum by variation of alpha from 0 degree to the 180 degree. Variation of alpha from 0 degree to the 180 degree. Means semi-controlled rectifiers or half controlled rectifiers Yes, we can vary the output voltage, but here point to be noted, the output voltage we can vary, it will be having only positive values. We can vary the output voltage from 0 volt to the maximum positive value, right? And by varying the alpha from 0 degree to 180 degree. As I said, these rectifiers consist of diodes and thyristors, right? Whereas the first one was uncontrolled rectifiers, output voltage was fixed. Here we can vary the output voltage, but the limitation is output voltage will be getting is only positive, Next we are having the type is a fully controlled rectifiers. Fully controlled rectifiers. So these rectifiers consist of only controlled switches, like a SCR. Okay, no diodes are used in this type of rectifiers. Okay, so here output voltage can be varied from 0 to the positive maximum and a negative maximum as well. So your output voltage varies from plus Vmax to the minus Vmax as well. Okay, by varying the firing angle alpha, right? Next, so fully controlled rectifier. So these are the classifications based on controllability of the output voltage. Next, let us discuss the classification based on rectification of input waveform. So based on the rectification of input waveform, there are two types. One is the half wave rectifier, second one is the full wave rectifier, right? So half wave rectifier and full wave rectifier. In the half wave rectifier, yes, either the positive half cycle or the negative half cycle of the supply will be rectified. The meaning is in the output will be getting the non-zero value only corresponding to either positive half cycle of the supply or negative half cycle of the supply. Are you getting the point, right? So it is the half wave rectifier. Next we are having the full wave rectifier. The full wave rectifier circuit that produces output voltage corresponding to both positive and negative half cycle. Here only positive or negative half cycle. Here positive as well as negative half cycle. Okay, will be rectified, right? Next, classification based on number of phases of input voltage. Okay, number of phases of input voltage. So we are having a single phase rectifier, 3-phase rectifier, or greater than 3-phase rectifier, that is a polyphase rectifier. Okay, so this classification is based on the number of input phases. So here input AC voltage applied to the rectifier may be single phase, 3-phase or polyphase. So accordingly we are having the rectifier classification as single phase rectifiers, 3-phase rectifiers and polyphase rectifiers, right? So yes, so phase controlled rectifiers, single phase converters, and here it is a 3-phase converter. So single phase converter means these are the rectifiers where the input is single phase. These are the rectifiers where the input is 3-phase. Okay, and in general again there are two types. Single phase rectifiers are having two types, uncontrolled rectifiers and controlled rectifiers. Okay, uncontrolled and controlled. And 3-phase rectifiers again it is having two types, uncontrolled rectifiers and controlled rectifiers. Converters means as long as today's topic is considered here, converters are nothing but a rectifier only, right? Next, now next classification is based on number of pulses in output voltage waveform. Okay, number of pulses in output voltage waveform. So friends, rectifier gives the output, that nature is it is a pulsating DC. Expectedly rectifier should give a constant DC waveform, but in a practical case whether we are getting the constant DC waveform, no, we are getting the output as a pulsating DC. If you recall, if you check the previous KPTCL questions, in one of the examination they asked the question like the output of AC to DC converter is, and they will give the options like it is a constant DC, it is a pulsating DC, it is a triangular, it is a sinusoidal, etc. Okay, so please keep it in mind, the output is a pulsating DC. Okay, pulsating DC. Why it is known as a pulsating DC, that you will understand while attending the online classes or the recorded videos as even. Okay, so now based on the number of pulses in the output voltage waveform, So corresponding to this, we are having the classification of rectifiers as single pulse rectifiers, 2 pulse rectifiers, 3 pulse rectifiers, 6 pulse rectifiers and 12 pulse rectifiers. Okay, so let us discuss the difference between these, right? So first one is the single pulse rectifier. Single pulse rectifier means one pulse in output voltage waveform corresponding to one cycle of the input. Means output voltage consists of only one pulse corresponding to the one input cycle. Now for the rectifiers, what is the input nature? It is a AC na. So corresponding to the one input cycle, if I am getting the output is only one pulse, then it is known as the single pulse rectifier. Single pulse rectifier. Okay. Next, 2 pulse rectifier. 2 pulse rectifier. For one cycle of input, yes, 2 pulses in the output voltage waveform. Okay, 2 pulses in the output voltage waveform. So here we are having single phase half wave rectifier and here it is single phase full wave rectifier. Single phase half wave rectifier gives only one pulse in the output voltage corresponding to one input cycle. So that's why it is known as the one pulse rectifier. Whereas single phase full wave rectifier gives 2 pulses in the output voltage corresponding to the one input cycle. Corresponding to the one input cycle. So that's why it is known as a 2 pulse rectifier. And in today's topic, we are going to discuss single phase half wave rectifier actually. Okay, we'll discuss that later on. Next is 3 pulse rectifier. So here corresponding to one input cycle, only one pulse in the output. Corresponding to one input cycle, 2 pulses in the output. So similarly here, corresponding to the one input cycle, in the output will be getting 3 pulses na. So that's why it is a 3 pulse rectifier. Is this clear? Right? Next one is the 6 pulse rectifier. So corresponding to the one input cycle, in the output will be getting 6 pulses. In the output will be getting 6 pulses. So that's why it is known as 6 pulse rectifier. So which rectifier gives the 6 pulses in the output? It is a 3 phase full wave rectifier. Which rectifier gives the 3 pulses in the output? It is a 3 phase half wave rectifier. Okay. Next, 12 pulse rectifier. So corresponding to the one input cycle, in the output will be getting 12 pulses. In the output will be getting the 12 pulses. So here, in order to achieve the 12 pulse rectifier, generally 2 6 pulse rectifiers are connected in series. Okay. Next, so single phase uncontrolled converters or rectifiers. I have shown here uncontrolled, half wave rectifier and full wave rectifier. So you can check here single phase uncontrolled rectifier. In that it is having a 2 types. One is the single phase half wave rectifier, single phase full wave rectifier. Single phase half wave rectifier means it is a 1 pulse rectifier, right? Single phase full wave rectifier is nothing but it is a 2 pulse rectifier. Next, 3 phase rectifier. It is having yes types. 3 phase half wave rectifier, 3 phase full wave rectifier and double star or 12 pulse converter. Okay. So here 3 pulse converter, that is a 3 pulse rectifier, 6 pulse rectifier and 12 pulse rectifier. So for single phase input supply, we will be achieving only single pulse rectifier and 2 pulse rectifier. But for getting the 3 pulse, 6 pulse and 12 pulse, we require a 3 phase input. Right? Next classification is based on quadrant of operation. So friends, if you recall the rectifier circuit or rectifier operation, generally which switch is preferred for a rectifier circuitry? Yes, we prefer a SCR, silicon controlled rectifier. In the case of controlled rectifier, SCR is preferred. And in the case of uncontrolled rectifier, yes, we are using a by default, that is the uncontrolled switch, that is nothing but the diode. So if you check SCR and a diode, both are the unidirectional switches. Both allows current in only one direction. So due to that, in the rectifier, load current is always positive. So here the output or load current of rectifier always remains in the same direction, that is nothing but the positive, right? In the rectifier circuitry, any rectifier circuitry you can check, for any load, the load current waveform or the load current value is always positive only. But we discussed some rectifiers gives the output voltage as a positive. Some rectifiers gives the output voltage positive as well as negative values. So depending on that, we are having the various quadrants of operation. So first one is the, yes, if the polarity of the average output voltage remains unchanged, that is nothing but V0 is always positive. We know load current is always positive, and if we are having the rectifier which gives only positive output, then we can say that that particular rectifier operates in only one quadrant. Means the rectifier gives the output voltage as a positive, output current as a positive, right? Yes, one example of this type of rectifier is whether we are having the rectifier which gives the output only positive and output current also, output voltage and output current both are only positive. Yes, we know all the rectifiers gives the output current only positive, and the rectifiers we discussed just like a single phase semi converters. This gives the output only positive values, now output voltage are only positive values, right? So here we are having all uncontrolled rectifiers, half controlled rectifiers or semi converters. These are the examples of single quadrant converters. They have asked the question, semi converters or half controlled rectifiers operates in dash dash quadrant. So always keep it in mind, the semi converters or half controlled rectifiers always operates in first quadrant. Why this is the first quadrant? Because semi converters or half controlled rectifiers gives the output voltage only positive. We discussed earlier, right? Semi converters or half controlled rectifiers changes the output voltage or varies the output voltage from 0 value to the positive maximum value by variation of alpha from 0 degree to the 180 degree. So output voltage will be only positive and output current we know it is a positive only. So that's why this quadrant of operation is the first quadrant, right? Second, we are having, yes, two quadrant rectifiers. Means the rectifiers which operates in the first and the fourth quadrant. Here if you check corresponding to the first quadrant and the fourth quadrant operation, we know rectifier consists of only unidirectional switches, so that's why load current is always positive. So load current is always positive and load voltage can be positive or can be negative. This can be achieved. So which type of rectifiers are giving the output voltage positive as well as negative? We discussed, yes, we are having the fully controlled rectifiers. Fully controlled rectifiers, yes, changes the output voltage from positive maximum to the negative maximum by the variation of firing angle alpha, right? So here, yes, if the output voltage polarity reverses, it operates in two quadrants 1 and 4, and the rectifier is also called as two quadrant rectifier. Example is all fully controlled rectifiers or full converters are the, yes, two quadrant rectifiers. They may ask the question, single phase fully controlled rectifier operates in dash dash quadrant. They may give the option like 1 and 2, 2 and 3, 1 and 4, 3 and 4, etc. So please keep it in mind, single phase fully controlled rectifiers always operates in first and the fourth quadrant. First and the fourth quadrant. Next we are having the four quadrant rectifiers or the four quadrant operation. So for that what we are doing, in order to achieve the four quadrant operation, simply we are connecting two fully controlled rectifiers in anti-parallel. Two fully controlled rectifiers are connected in anti-parallel, and the anti-parallel connection of two fully controlled rectifiers, yes, it is known as a dual converter. It is known as a dual converter. In detail we will discuss while discussing that dual converter particular topic, okay? So the thing here is, we are having the fully controlled rectifier, it gives the first and the fourth quadrant operation. If I add one more fully controlled rectifier and if I connect that in anti-parallel with a first fully controlled rectifier, then I can achieve the four quadrant operation. I can achieve the four quadrant operation, right? Next, applications of rectifier. So we know rectifier is one of the important converter in a power electronics. So what are the applications of rectifier? Yes, rectifiers are used in a DC motor drives, in a HVDC transmission, yes or no, right? So let us discuss applications of rectifiers. DC motor drives. We know drive, in a electrical engineering we are having a different area, that is a drive. Drive is nothing but the motion control. Electrical drive is nothing but the speed control of electrical motor, right? So DC motor drives means what? Here we are interested in controlling the speed of DC motor, but how? By using the power electronic converters. In your second year you might have studied the speed control techniques of or methods of speed control of DC motor, right? There you might have heard the flux control, armature resistance control, etc. Okay, but those were the conventional approaches. In a DC motor drives or in a drive subject, you might have come across the DC motor drives. So here what we are doing, we are controlling the speed of DC motor only, but how? With the help of power electronic circuitries. So in the DC motor drives, the rectifier is used. Next is the HVDC transmission, high voltage direct current transmission. If you recall the circuitry of the HVDC transmission, yes, at the generating side or at the sending end, we are having the AC supply. That AC we are converting into the DC. So how to convert the AC to DC? The AC to DC can be converted with the help of rectifier. And that DC we are transmitting over a long distance. And at the sending end, at the receiving end, again we are converting that DC to the AC. So that's the DC to AC is nothing but your inverter. So in the HVDC transmission system, we are using the rectifier as well as inverter. So one application of rectifier circuitry is a HVDC transmission, right? Next one is the battery charging circuit. Yes, battery charging circuit. Traction system working on DC, right? The traction system, electric traction, where the DC motors are used, right? In that case, we need to go for the rectifier circuitry. Apart from this, UPS, uninterruptible power supply, heating loads, etc. Now coming towards the today's topic, let us discuss single phase half wave controlled rectifier with a purely resistive load. Very simple circuitry, but today we are going to analyze it in depth. We are going to analyze it, and which kind of questions you may get, that we are going to discuss here. Okay, so single phase half wave controlled rectifier with a purely resistive load. So circuit diagram for single phase half wave controlled rectifier with a purely resistive load. So as this is the rectifier, so input should be AC only, right? So here input is AC, which is equal to Vs, which is equal to Vm into sine of omega t. So here we are having a pure sinusoidal supply. Next, we are discussing this for purely resistive load. So here load is a R load, resistive load, right? Apart from the supply and a load, we are using one more element, that is nothing but this a thyristor T, right? Consider this is a thyristor T. So for that, before moving towards the circuit operation, we need to recall, yes, some concepts or some important points related to the thyristor. Thyristor is, strictly speaking, it is a family of devices which consist of 4 layers and 3 junctions. In the thyristor family, which is the most popular device, come on, in a thyristor family, which is the most popular device, can anyone? In a thyristor family, which is the most popular device? Yes, in a thyristor family, which is the most popular device? You can send your answers in the chat box. Yes, we are having the various members in a thyristor family like SCR, GTO, TRIAC, etc. Which is the most popular device? Yes, Basavaraj. SCR, very good. So SCR is the most popular. Very good. Moksha Gundam Ishwasara. Yeah. Nice to meet you. Okay. SCR is the most popular device, right? Silicon controlled rectifier. So you might have seen in most of the books, generally the SCR and the thyristor, these terms they have used interchangeably. Okay. You can refer any book. In most of the books they have interchangeably use the terms SCR and thyristor. Okay, so suppose here we are using the SCR, that is the silicon control rectifier, or it is also known as a thyristor. It is also known as a thyristor. So very simple circuitry we are having. In this we are having a supply voltage Vs, which is a pure sinusoidal. Load is a purely resistive. Apart from the supply and a load, we are using one switching device, that is a thyristor or a SCR. Now recall some points related to the SCR. Yes, SCR is having how many terminals? Come on. SCR is having how many terminals? Yes, you can post your answers in the chat box. SCR is having how many terminals? One, two, three, four, five. Yes, how many terminals SCR will be having? Yes, Basavaraj, 3. Mokshagundam Vishwashraya. Yes, 3. Right. Which are those 3 terminals? We know it is a anode, cathode and gate. Okay. SCR is a 3-terminal device. It is having a 3 terminals named anode, cathode and gate. Right. Between anode and cathode, generally the load circuitry is connected na. Right. So if you check this SCR, here we are having terminals like anode, this is a cathode and this is a gate terminal. So friends, if you check between anode and cathode, we are having the load circuitry, that is a high power circuitry, high current circuitry, high voltage circuitry. Between anode and cathode, load circuitry is connected. And between gate and cathode, yes, low power circuitry is connected. That circuitry is known as the controlling circuitry. Yes or no? So for SCR, let me write here. For SCR, between anode and cathode, yes, we are having a load circuitry. Load circuit is connected. Load circuit is connected, right? Whereas between gate and cathode, yes, which circuitry is connected? Controlling circuitry is connected. Controlling circuitry is connected. You might have come across the BJT, right? Bipolar junction transistor. In a BJT, we are having the 3 terminals na? Which are those 3 terminals? Yes, base, collector, emitter, right? So here in the BJT, generally we connect between collector and emitter, the load circuitry is connected na? And whereas between base and emitter, the controlling circuitry is connected. So similarly in the SCR, between anode and cathode, the load circuit is connected, and between gate and cathode, the controlling circuit is connected. The purpose of the controlling circuitry is control the conduction of the switch, to turn on the switch, to turn on the SCR. That is the basic function of the gate and cathode circuitry. You might have heard in the SCR we are having very famous method of triggering. Yes, that method is gate triggering. Yes or no? Right? In the gate triggering, what we are doing? We are connecting a circuitry between gate and cathode terminals, right? And we are circulating the small amount of the gate current in the gate cathode circuitry. Okay, and accordingly our SCR may turn on at various instants. Definitely we are having a various methods of turning on, just like a forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering, light triggering, etc, etc, etc. But in that, which is the most popular method? The most popular method is a gate triggering. Yes or no? Gate triggering. So here, as here we have shown, the gate cathode terminals are open, but please assume that between gate and cathode the controlling circuitry is present. Okay, assume that between gate and cathode the controlling circuitry is present. By observation you can say that, sir, these two are the open circuit here, and how we are saying that the gate current is circulating between the gate and cathode. So this is our assumption gate cathode circuitry we have not shown here, or in any book you can check. Generally gate cathode circuits are not shown, but we need to assume that the circuitry is present. So let me write here, our assumption is assume controlling circuitry is present. Assume controlling circuit is present between gate and cathode. Between gate and cathode. Between gate and cathode. Right? So this is the circuitry we are having. Yeah. Between anode and cathode, the load circuitry is directly connected, and gate and cathode, let us assume that controlling circuitry is present. Now, voltage, supply voltage is Vs, which is equal to Vm into sine of omega t. That is a pure sinusoidal voltage. Vs is equal to Vm into sine of omega t. Supply voltage, pure sinusoidal voltage. Expected output of the rectifier is a constant DC. It should be ideal DC. But let us check whether our rectifier circuitry is giving the constant DC or not. Okay. Now, Vs supply voltage, Is supply current. Let us consider voltage across thyristor is Vt. The voltage across thyristor is said to be positive if anode is at a more potential than that of the cathode. Current flowing through thyristor, let us consider it is a It. Voltage across load V0. V0 is said to be positive if upper terminal is at higher potential, lower terminal is at a lesser potential. I0 is the load current. I0 is the load current, right? Now coming towards the waveform. Yes. Supply voltage Vs, which is equal to Vm into sine of omega t. Just now we have written na? Vs is equal to Vm into sine of omega t. So during omega t is 0 to pi, Vs is positive. During 0 to pi, Vs is positive. Pi to 2 pi, Vs is negative. 2 pi to 3 pi, Vs is again positive. So in the supply voltage waveform, we are having alternate positive, negative, positive and negative cycles. Next, Ig, that is the gate current. So gate current means, as I said, between gate and cathode, let us assume the controlling circuit is present. So Ig is a non-zero. So here we are applying the gate pulse to the SCR, right, at omega t is equal to alpha. Now we will discuss why we have applied the gate pulse only during the positive cycles of the supply, why we have not applied the gate pulse during the negative cycle of the supply. We are going to discuss. Next, V0 load voltage, I0 load current, Vt voltage across the thyristor. Okay. Now let us discuss one by one. So here we are having the circuitry, right? Vs is Vm into sine of omega t. So we know Vs is having a positive cycle, positive cycle and negative cycle. So suppose when Vs is positive, let us consider the polarities plus here and minus here. I am saying that when Vs is having a positive values, then I am considering that upper terminal is at a higher potential, this lower terminal is at a lower potential. Okay. So when Vs is positive, polarity will be like a plus here and a minus here. So it is like this is the highest potential point in the circuit. This is the lowest potential point in the circuit. Yes or no? Right? This we are discussing for Vs positive. So when Vs is positive, this is at higher potential, this is at lower potential. So higher potential, whatever the potential here, the same potential appear at the anode of thyristor. Right? Whatever the potential is present, the same potential will appear through the load at the cathode of thyristor. Initially our thyristor will be in an off state. So if you check, why we are applying the gate pulse? We are applying the gate pulse in order to turn on the SCR, na? Right? So initially when SCR is in an off state, means it is like acting as an open circuit. If this is acting as an open circuit, what about the circuit current? Circuit current will be 0. If circuit current is 0, what about the load current? Load current is also 0. If load current is 0, what about the load voltage? According to Ohm's law, V0 is equal to I0 into R. If the load current is 0, load voltage is also 0. So please try to understand, when SCR is in a off state, circuit current is 0, so load current is 0, load voltage is 0. Load voltage is 0, the meaning is potential difference between this point and this point is a 0. Potential difference is 0 means, can I say that whatever the potential here, the same potential will appear at this point? So potential difference is 0. Difference is 0. Difference between potential at voltage at this point or potential at this point and potential at this point. This difference is nothing but the potential difference. So if the potential difference is 0 means, can I say that this potential is equal to this potential, right? So here, if these two potentials are same, you can check here. Here we consider the lesser potential. Same potential will appear here. Same potential will appear here. Same potential will appear here. Same potential, and same potential. Means whatever the potential is here, the same potential will appear at the lower terminal of the load. And as the potential difference across the load is 0, so this potential is equal to this potential, and again the same potential will appear at the cathode. So please keep it in mind. If SCR is in an off state, load voltage is 0, whatever the supply voltage present here, right, higher potential will appear at the anode of the SCR, lower potential will appear at the cathode of the SCR. Now, if anode is at higher potential than that of the cathode, whether SCR will be in a forward bias mode or reverse bias mode? Yes, can anyone? Yes. For the SCR, if anode potential is greater than the cathode potential, SCR will be in forward bias mode or reverse bias mode? Come on. Please post your answers in the chat box. The SCR, if anode potential is greater than the cathode potential, SCR will be in a forward bias mode or reverse bias mode? Yes, it is a forward bias mode. Mokshgundam, correct. Anode is at higher potential than that of the cathode, SCR is said to be in a forward bias mode. So here, can we say that when Vs is positive, SCR will be in a forward bias mode because anode is at a higher potential than that of the cathode. So let me write here. When Vs is a positive, very important, SCR is in forward bias mode. SCR is in forward bias mode. SCR is in forward bias mode. SCR is in forward bias mode, right? Now recall from the gate triggering. If I want to turn on the SCR with the help of gate signal, with the help of gate current, the very first requirement is SCR should be in forward bias mode, yes or no, right? So here if you check this waveform, when Vs is positive, SCR will be in a forward bias mode. So in order to turn on the SCR, we are going to apply the gate signal, we are going to apply the gate pulse to the SCR. Similarly, you can check for the next positive cycle, that is from 2 pi to 3 pi. Again Vs is positive. So Vs is positive means SCR will be in a forward bias mode again. So when SCR is in forward bias mode, again we are going to apply the gate pulse to the SCR. Right? Similarly, you can check for 4 pi to 5 pi and so on. Now let us discuss when Vs is negative, what will happen? When Vs is negative, what will happen? So if Vs is negative, means it is like a minus here and plus here. If Vs is negative means minus here and plus here. So it is like this is the lowest potential point, this is the highest potential point. Lowest potential will appear at the anode of the SCR. Highest potential will appear at the cathode of the SCR. So can we say that when Vs is negative, SCR will be in a reverse bias mode. Yes or no? Vs negative means anode is at a lesser potential than that of the cathode. So SCR will be in a reverse bias mode. So point to be noted. When Vs is negative, SCR is in reverse bias mode. SCR is in reverse bias mode. SCR is in reverse bias mode. So my question is, if SCR is in a reverse bias mode and if I apply the gate signal, whether the SCR will turn on? Come on, please post your answers in the chat box. If SCR is in a reverse bias mode and if we apply the gate pulse to the SCR, whether the SCR will turn on? Yes or no? Yes, you can post your answers in the chat box. When SCR is in a reverse bias mode and if we apply the gate pulse to the SCR, yes, whether our SCR will turn on? No, right. Chandan Gowda, Yogesh, good. No, right. So, important point here. When SCR is in a forward bias mode and if we apply the gate pulse, then and only then SCR will turn on. If SCR is in a reverse bias mode and if I am applying the gate pulse to the SCR and I am expecting that SCR should turn on, no, it is a meaningless. SCR will not turn on at all. Because for that you need to recall the SCR construction. SCR is a PN device, na? So when SCR is in a reverse bias mode, junction J1, J3 reverse bias, junction J2 forward bias. Yes or no? So you can check J1, J3 are in reverse bias, J2 in a forward bias, and if you apply the positive gate signal, positive gate current if you circulate, your junction J1 will not reduce the depletion layer. Okay? So that's how our SCR will not turn on when reverse bias, when the voltage across SCR is negative, that is SCR is in a reverse bias mode. So please keep it in mind. So when Vs is positive, we apply the gate pulse to the SCR. When Vs is negative, SCR is in a reverse bias mode. So we cannot turn on the SCR by using the gate signal. So that's why during negative values of the supply voltage, we have not applied the gate pulse to the SCR. Similarly again, when Vs is positive, we are going to apply the gate pulse. When Vs is negative, gate pulse is not applied to the SCR. Is this clear to all? Right? So when Vs is positive, then and only then we are going to apply the gate pulse to the SCR. Right? Now, here, suppose this angle omega t, right? This x-axis is nothing but the angle, that is the omega t. So at omega t is equal to alpha, we are applying the gate pulse to the SCR, right? So before alpha, you can check between 0 to alpha, between omega t is equal to 0 to alpha, Vs is positive, but whether we have applied the gate pulse, no. So what will happen to the SCR, let us discuss, okay? During omega t is equal to 0 to alpha, during omega t is equal to 0 to alpha, what is the Vs value? It is a positive. Vs is a positive. But whether the gate pulse is applied? No, gate pulse is not applied. Gate pulse is not applied to SCR. Gate pulse is not applied to SCR. So my friends, SCR is in a forward bias mode, and if the gate pulse is not applied, then what will be the mode of operation of SCR? Come on, recall from the static VI characteristics of SCR. In the static VI characteristics of SCR, we are having the three modes of operation. Na? First one is forward blocking. Second one is forward conduction. Third one is the reverse blocking. So out of these three modes, yes, SCR will be in which mode during 0 to alpha? Come on. During 0 to alpha, SCR will be in which mode? You can post your answers in the chat box. During 0 to alpha, what is the mode of operation of SCR? SCR is in a forward bias mode, but the gate pulse is not applied. The meaning is SCR is in a forward bias mode and it is in a off state. So it will be in, whether it will be in a forward blocking mode or forward conduction or reverse blocking. Which mode? SCR is in a forward bias mode, but gate pulse is not applied. Yes. So the mode of operation is forward, correct. Forward blocking mode. Good, good, good. Chandan Gowda, good. So SCR will be in a forward blocking mode. Very important. SCR will be in a forward blocking mode. Forward blocking mode. So if SCR is in a forward blocking mode, means it is like SCR is in a off state. SCR is in a forward bias mode, but gate pulse is not applied, means it is in a off state. Forward blocking means SCR is in a off state. So equivalently, can we draw the circuitry during this interval? Yes, we're having the circuitry like this. SCR is in a forward blocking mode. The R, V0, VT, IT, IS, VS. Yes, right? So this is the equivalent circuitry during omega t is equal to 0 to alpha. SCR is in a off state, forward bias mode, but it is in a off state, forward blocking mode. So if SCR is in a off state, whether the current will flow from source towards the load? No. So can we say that circuit current is 0? That is nothing but IS, IT and I0. This current is I0, na? So here can we write during this mode IS is equal to IT is equal to I0 is equal to 0 ampere. Circuit current is 0 because circuit is an open circuit, na? Right? Closed path is not available. So that's why circuit current is 0. Now I0 is 0. So according to Ohm's law, what is V0? V0 is equal to I0 into R. V0 is equal to I0 into R, which is equal to 0 into R. That is nothing but 0 volt. So point to be noted. Output voltage is 0. Output current is also 0 ampere. Right? So circuit current, that is nothing but supply current, thyristor current and load current all are 0. Load voltage is also 0. Can we find the thyristor voltage VT value? Yes, simply apply KVL to this loop. Apply KVL to this loop. Yes, what is the KVL equation? Plus Vs minus Vt minus V0 is equal to 0. Right? So let me apply KVL to loop. KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0. In this, what is a V0? V0 is 0, right? So this term is a 0. So can I write Vt is equal to Vs? The meaning is voltage across thyristor is the same as that of the supply voltage. So you can check the waveforms during 0 to alpha. V0 0, I0 is 0. So during 0 to alpha, V0 is 0. During 0 to alpha, I0 is also 0. And during 0 to alpha, Vt is same as that of the supply voltage. You can check supply voltage waveform is like this. It is increasing. So same waveform we are having for the Vt also. Okay. So this voltage across thyristor waveform is the same as that of the supply voltage. Right? Next, at alpha we are going to apply the gate pulse to the SCR. So as soon as the gate pulse is applied to the SCR, our SCR will turn on. Right? So during omega t is alpha to pi, what will happen in the circuit? Let us discuss. Okay, so we had this type of circuitry. At alpha, I am going to apply the get pulse to the SCR. Alpha, you can check, corresponding to the alpha value, supply voltage is positive, means SCR is in a forward bias mode only, right? So at alpha, when the get pulse is applied to the SCR will turn on immediately. Once SCR turns on, it is like SCR will act as a short circuit. So current will flow from source towards the load. Okay, so during omega t is equal to alpha to pi, during omega t is equal to alpha to pi, during alpha to pi, yes, SCR is in which mode? Forward conduction mode, right? Because we have applied the get pulse to the SCR will act as a short circuit. So mode of operation of SCR is a forward conduction mode. SCR will be in a forward conduction mode. Forward conduction mode. Forward conduction mode. So during this interval, can we draw the equivalent circuit? Yes. So it is like this. SCR is acting as a short circuit on state. Na conduction mode means it is in a on state. Supply voltage Vs, voltage across thyristor Vt. Vs is positive. This current is Is. It is 0. And here it is a I0. Yes or no? During alpha to pi, SCR will be in a conduction mode, forward conduction mode. SCR will be acting as a short circuit. Current will flow from source towards the load through this thyristor. Now thyristor is in a conduction mode. So what is the voltage across thyristor? It is a 0. Vt is equal to 0 volt. While analyzing the circuit, yes, we are considering that in the circuit, whatever the SCR is present, that SCR is the ideal SCR. Okay, that's why the on state voltage drop is 0, right? So Vt is equal to 0. Next, Vt is 0. So can I write V0 value? Yes. How to write V0 value? Simply apply KVL to this loop. KVL to the loop. Yes. KVL to loop. KVL to loop. Come on. What is the KVL equation? Plus Vs minus Vt minus V0 is equal to 0. Yes or no? Right? Minus to plus, so it is a plus Vs. Plus to minus, so it is a minus Vt. Plus to minus, so it is a minus V0 is equal to 0. KVL, Kirchhoff's voltage law. In that, Vt is 0. So can I write here Vt is a 0? So if Vt is 0, can I write V0 is equal to Vs? Yes. V0 is equal to Vs volt. That is, output voltage is same as that of the supply voltage. Right? Now, according to Ohm's law, we know V0 is equal to I0 into R. So what is the I0? V0 divided by R. Right? So let me write here, load current I0 is equal to V0 by R, which is equal to Vs by R. Okay, load current is equal to Vs by R. Now, if you check this circuitry, we are having only one loop. Yes or no? We are having only one loop. So, can I write I0 is equal to It is equal to Is? Yes or no? You can check. Only one loop we are having, and I have considered the branch currents like this is the Is, this is the It, this is the I0. Whatever the current here, the same will flow here, the same will flow here. Means we can write I0 is equal to It is equal to Is. So now Is is equal to It is equal to I0, which is equal to Vs by R. Which is equal to Vs by R. Means source current, thyristor current and load current all are same. All are same. Right? So during omega t is alpha to pi, in the conclusion we are having V0 is equal to Vs, Vt is 0 and I0 is equal to Vs by R. So you can check the waveforms. You can check the waveforms here. During alpha to pi, What is V0? It is same as that of the supply voltage. It is same as that of the supply voltage. So here V0 is the same as that of the supply voltage during alpha to pi. During alpha to pi, what is the I0? I Vs by R now we have written. It is equal to Vs by R. Vs is the supply voltage. So supply voltage waveform, and if I divide this waveform with R, the nature will be like this, same only, right? So I0 waveform will be in phase with the V0, in phase with the V0, right? So this is like a Vs by R. This is a Vs by R. What are the Vt? Vt is 0. So alpha to pi Vt is a 0, right? Now, at equal to pi, at omega t is equal to pi, what is happening? Supply voltage value is reaching the 0 value. Yes or no? Vs becomes 0. So at omega t is equal to pi, Vs is equal to 0. Let me write. At omega t is equal to pi, Vs is equal to 0 volt. So if Vs is 0 volt, what about the V0? You can check between alpha to pi, V0 is equal to Vs we are having, right? So therefore, V0 is equal to Vs is equal to 0 volt. So load voltage also reaches the 0 value. Load voltage also reaches the 0 value, right? So now load voltage is 0. So what are the load current? Yes, definitely it will be 0. I0 is equal to V0 by R, which is equal to 0 by R, means 0 only. So it is equal to 0 ampere. So I0 also equal to 0 ampere. What about the supply current? Now we know supply current, thyristor current, load current all are same na? So therefore if I0 is 0, we can write Is is equal to It is equal to I0, all are 0 ampere, all are 0 ampere. So friends, very important point here. If you check at omega t is equal to pi, supply voltage is reaching 0 value. So due to that your thyristor current is also reaching the 0 value. Now if you recall the commutation of SCR, in a SCR commutation we are having a two-step procedure na? What is that procedure? The first thing is, in order to turn off the commutation is nothing but turning off of a SCR. In order to turn off the SCR, the first thing is we need to reduce the anode current value below to that of the holding current value. Anode current means thyristor current, right? So here at omega t is equal to pi, thyristor current is becoming 0 value, 0 ampere. The meaning is thyristor current is reaching the lesser than the holding current value. So the first condition for commutation has reached. Now after that, the second requirement is we need to maintain the reverse voltage across the SCR. We need to maintain the reverse voltage across the SCR. Actually, the study of switching devices, that will be covered in the chapter number 1, right? Switching devices chapter. And this is the next to the switching devices chapter, na, rectifier we are having. Okay. So I am here assuming that you are familiar with the SCR, right? So in order to turn off the SCR, we are having the two-step procedure. The first step is we need to reduce the SCR current less than the holding current value, and second step required is we need to maintain the reverse voltage across the SCR, okay, for the time Tc, which is greater than or equal to Tq actually, okay. That Tc, Tq we will discuss it in some of the later on in one of the lecture, okay. Nice, right. So It is equal to 0 ampere. So here thyristor current becomes 0. Now after pi what will happen? After pi supply voltage is negative. You can check after pi supply voltage is negative. So we know when supply voltage is negative, thyristor will be in a reverse bias mode. So during pi to 2 pi, during omega t is equal to pi to 2 pi, let me write here. During omega t is equal to pi to 2 pi, supply voltage is negative. Supply voltage is negative. Yes, SCR will be in which mode? Reverse blocking mode. SCR will be in reverse blocking mode. Reverse blocking mode. Yes or no? So reverse blocking mode means SCR will be in a off state. So equivalent circuit we can draw during pi to 2 pi. Supply voltage is negative, SCR is in a reverse blocking mode means SCR will be in a off state. minus plus, right? This is Vt, It, I2 and V0, right? So here please try to understand. During pi to 2 pi, Vs is negative. So I have reversed the polarity of the supply voltage. Here it is plus, here it is minus. You can check during 0 to pi, it was like upper terminal positive, lower terminal negative. But during pi to 2 pi, Vs is negative. So that's why lower terminal positive, upper terminal negative. Thyristor will be in a reverse blocking mode. So thyristor is in a off state. Okay. Next, here if thyristor is acting as an open switch, what about the circuit current? 0. So we can write Is is equal to It is equal to I0 is equal to 0 ampere, right? Is, It, I0 all are 0 ampere. Yes or no? Now I0 is 0. What about the V0? V0 is equal to I0 into R, which is equal to 0 volt. It is equal to 0 volt. Yes or no? Right? Now V0 0 volt, I0 is 0 ampere. Now can we write Vt value? Simply apply KVL to this loop. KVL to the loop. KVL to loop. It is a minus Vs minus Vt minus V0 is equal to 0. In this V0 is 0. So we are having V0 is a 0. So therefore we can write Vt is equal to minus Vs. The meaning is voltage across thyristor is a negative. Voltage across thyristor is a negative. So from pi to 2 pi, you can check the waveform. During pi to 2 pi, V0 is a 0, I0 is a 0 and Vt is a negative. Vt is a negative here, right? Its value, its nature will be same as that of the supply voltage, but it is a negative. Right? So here you can check at omega t is equal to pi, current flowing through thyristor becomes the 0, right? And after that, if at pi current flowing through thyristor becomes 0, after that you can check the Vt waveform, it is a negative from pi till 2 pi. From pi till 2 pi, Vt is a negative. The meaning is the reverse voltage will be maintained across the SCR. So that's why our SCR will successfully turn off. Our SCR will successfully turn off. So what is the nature, what is the type of the commutation here? Yes, can anyone? In this circuitry, what is the type of commutation? Yes, in this circuitry, what is the type of commutation? Come on, what is the type of commutation? Is it a natural commutation or forced commutation? Yes, Mokshagundam. It is a natural commutation. Yes or no? Right? Here thyristor is turning off due to the nature of the supply. Right? In order to turn off the thyristor, whether here we are adding any external element? No. Right? So that's why it is the natural commutation. Always keep it in mind. In the case of rectifier or the power electronics converters, where input is a AC, in that case the commutation is natural commutation. If SCR is used, then commutation will be natural commutation. So which circuitries or which converters we are having in which we are using the AC input? We are having the rectifier, we are having the AC to AC converter, that is the AC voltage regulator, right? So for these two circuitries, generally the natural commutation is possible, okay, or achieved, you can say. These type of circuits also, these type of questions also they have asked, okay. The commutation, type of commutation in rectifier is, it is a natural commutation, right? So this will continue till 2 pi. After 2 pi, what will happen? Again the same cycle repeats, yes or no? You can check. After 2 pi, whatever the waveform we are having for V0 here during 0 to 2 pi, the same is repeating from 2 pi to 4 pi. Similarly, check for I0 also. Whatever the waveform we are having from 0 to 2 pi, same is repeating from 2 pi to 4 pi. Similarly, for Vt also, the waveform for 0 to 2 pi, the same will be appearing or repeating from 2 pi to 4 pi, 2 pi to 4 pi. Is this clear? Right? So friends, let us take a short break here, okay? 2 to 3 minutes break, and after that we will discuss how to derive the expressions, because expressions are very important, like a average value of output voltage, RMS value of output voltage, average load current, RMS load current, average value of load power, conduction time of thyristor, circuit turn off time of thyristor, peak inverse voltage rating of thyristor, input power factor, etc. Okay, so these are the important expressions and these are very interesting. Okay, so please don't miss the session. We will take a break, short break of 2 to 3 minutes, and after that again we will resume. Right. So welcome back. So till now we have discussed the circuit operation. So before proceeding towards the derivations, let us check what is the nature of output voltage. This is the rectifier circuitry. It converts AC to DC. Yes or no? So here input is AC. AC means what? It is having a positive as well as negative values. Yes or no? You can check. Supply voltage is a AC. It is having a positive as well as negative values. AC means any waveform that is a alternating. Alternating means it is having alternate positive, negative values. It is not like only sinusoidal is a AC waveform. No. Triangular waveform, square waveform, right? These are also the examples of AC waveform. But here we have considered a input supply is a pure sinusoidal, because in real life also in India we are having the easily available supply is a AC supply. In that single phase AC and three phase AC we are having. Okay, so here we consider the single phase AC supply. And what is the nature of the AC supply available? AC supply is nothing but whatever the supply we are getting from electricity board. That is the sinusoidal supply now. So that's why we consider the sinusoidal supply. That is a single phase AC supply as an input. Okay, that is the pure sinusoidal waveform. Now it is having positive as well as negative values. The meaning it is a AC waveform. Now you can check the V0 waveform. Expectedly our rectifier circuit should give the constant DC na. But whether our output, whether our practical rectifier is giving the constant DC, no. You can check, it is having a values like 0, positive, 0, positive. So values are either positive or 0, positive or 0. Means only positive values are present here. Whether the negative values are present, no. So that's why output voltage is a DC. Output voltage is a DC. But whether it is a flat DC, no. Right? It is a pulsating DC type of waveform we are having. Okay, we are having the pulses. We are having the pulses. Next, so output is a DC, input is a AC. Now, corresponding to one input cycle, you can check from omega t is equal to 0 to 2 pi. From omega t is equal to 0 to 2 pi. We are having the one cycle, right? One cycle of the input voltage. One cycle of the input voltage. So corresponding to 0 to 2 pi, we are having one cycle of the input voltage, and corresponding to the one cycle of the input voltage in the output, how many pulses we are getting? We are getting only one pulse na? Yes or no? Corresponding to one input cycle, in the output we are getting how many pulses? We are getting only one pulse. We are getting only one. This is a pulse. This is a pulse, right? So we are getting only one pulse. So that's why it is also known as single phase one pulse rectifier. Are you getting the point? It is also known as a single phase one pulse rectifier. Why it is a one pulse? Because corresponding to one input cycle, in the output we are getting only one pulse. We are getting only one pulse, right? Now my question is, sometimes they ask the question, if supply frequency is a Fs, if supply frequency is a Fs, then what will be the pulse frequency of the output voltage? If the supply frequency is Fs, then what will the pulse frequency of the output voltage? Come on. What will the pulse frequency of the output voltage? Please try to answer the question. Very important question. They have asked this type of questions in a previous examinations. Okay. Come on. If the supply frequency is a Fs, then what will the output pulse frequency? Just now we discussed corresponding to one input cycle. In the output we are having only one pulse na? So what is the output pulse frequency? If supply frequency is Fs, what is the output pulse frequency? You can post your answers in the chat box. Yes, if supply frequency is Fs, what is the output pulse frequency? Whether it will be same as that of the supply frequency or it will be different. Come on. Supply frequency is Fs. The meaning is corresponding to 1 second. The supply is completing how many cycles? Fs cycles, na? Right? Suppose Fs is 50 Hz. In India, we are having the standard frequency is 50 Hz, na? In US, it is a 60 Hz. But in India, it is a 50 Hz. Suppose we are having, Mahadev Gamma is saying Fs by 2. No. Suppose Fs is equal to 50 Hz. Let us consider. Listen, very important bit. What is the meaning of Fs is 50 Hz? The meaning is supply frequency is 50 Hz. Means in a 1 second, supply is completing how many cycles? 50 cycles. Yes or no? So in 1 second, if my supply is completing 50 cycles, this is the 1 cycle, this is the 2nd cycle. Similarly, we are having the 3rd cycle, 4th cycle and 50th cycle. So in 1 second, supply is completing 50 cycles. And we know corresponding to 1 cycle of the input, in the output, how many pulses we are having? We are having a 1 pulse only, na? For 1 cycle, we are having 1 pulse. For a 2nd cycle, again we are having a 1 pulse. So for 50 cycles of the supply, in the output, how many pulses will be getting? Definitely will be getting the 50 pulses, na? You getting the point, right? For 1 cycle, 1 pulse. So for 50 cycles, we will be having the 50 pulses in the output. So my dear friends, if your supply frequency is a 50 Hz, definitely the output pulse frequency is also equal to 50 Hz only. Is this clear? So in general, if supply frequency is Fs Hz, can we say that output pulse frequency is also equal to Fs Hz only? Yes or no? They have asked the question in a previous examinations. Okay? If the supply frequency is a 50 Hz, then what will the output pulse frequency? So always keep it in mind, as this is the single phase single pulse SCR, means one input cycle we are having only 1 pulse in the output. So definitely for Fs cycles we will be having the Fs pulses. So that's why the output pulse frequency is always equal to supply frequency. Let me write, output pulse frequency is equal to supply frequency. Very important point. Output, O/P means output. Output pulse frequency. Pulse frequency is equal to supply frequency. Supply frequency. Yes. What is the another name for this rectifier circuitry? It is also known as single phase, single pulse. Single phase, single pulse rectifier. Single phase indicates, single phase means input supply is single phase AC supply. Single pulse means corresponding to 1 input cycle, in the output we are getting only 1 pulse. So that's why it is a 1 pulse, right? So single phase single pulse rectifier. So always keep it in mind. In single phase single pulse rectifier, output pulse frequency is equal to supply frequency. Output pulse frequency is the supply frequency, right? Next, what is the nature of the output? Output is pulsating DC, right? Or let me write, nature of output. Nature of output is pulsating DC. It is not a flat DC, be careful. It is a pulsating DC. They have asked the question in a previous examinations, right? AC to DC converter that gives the output, and options will be like a flat DC, pulsating DC, triangular, sinusoidal, etc. Okay? So always keep it in mind, it is a pulsating DC. It is a pulsating DC, right? So next, now let us discuss how to derive the expressions. As this is AC to DC converter, right? As this is the AC to DC converter. So input is AC, output is a DC. In the AC, in the AC, what is the effective value? It is the RMS value, na? You can check in your home also. You might have come across the available supply single phase 230 volt 50 hertz, na? What is that 230 volt indicates? That 230 volt is a RMS value. Yes or no? Right? So please keep it in mind. In AC, whatever the by default value we denote there, we write there, that is your RMS value. So in AC, the effective value is RMS value. Whereas in a DC, the effective value is an average value. In a DC, effective value is an average value, right? So here we are going to discuss how to derive the average value of output voltage, or it is also known as DC output voltage, right? In a DC, what is the effective value? Average value. So that's why we have used here average output voltage, or it is also known as a DC output voltage. Now, for that, recall the V0 waveform. How is the V0 waveform? Yes, we are having the V0 waveform like this. Yes, here it is the V0 waveform. This waveform is having 0 to 2 pi. Whatever the waveform, we are having the same waveform repeats from 2 pi to 4 pi, right? So periodic angle of this waveform is a 2 pi. Corresponding to 2 pi radian, how many pulses we are having? We are having only one pulse. So we can write it as 1 by 2 pi. Let me write here. Yes, V0 average. 1 by 2 pi. Integration from 0 to 2 pi. V0 into d omega t. Please try to understand the meaning of this expression. Suppose we are having a 10 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How generally we find the average value of those 1 to 10 numbers? We add the numbers, na? 1 plus 2 plus 3 plus 4 plus up to the plus 10. We add and again we divide it with the total number, that is a 10. Na? So it is like 1 plus 2 plus 3 plus up to the 10 divided by 10, right? So now this is that was the manual operation we were doing, and that manual operation we can use in order to find the average value when we are having only discrete numbers, we are having some samples. But in this case, you can check the V0 waveform we are having. It is a continuous signal, na? Right? So in this V0 waveform, if you check 0 to 2 pi, whatever the periodic angle we are having, in that we are having the 3 sub intervals, 0 to alpha, alpha to pi, pi to 2 pi. Definitely 0 to alpha and pi to 2 pi, V0 is 0. So its addition will be 0, right? Addition of instantaneous values of V0 over 0 to alpha is 0. Over pi to 2 pi is also 0. But from alpha to pi, V0 is a continuous type of waveform. So if this is a continuous type of waveform, alpha to pi, then how many discrete samples we will be having? We will be having the infinite samples, na? So can we add the infinite samples one by one manually? No. So in order to add that, we are taking the help of mathematical operator, that is the integrator. Integrator means what? Integrator is like a integration, integrate, that is nothing but add. Yes or no, right? So you can check here V0 average. While writing the V0 average expression, we have written it is integration over 0 to 2 pi V0 into d omega t. What this indicates? Integration over 0 to 2 pi V0 into d omega t. That is nothing but this is your addition of V0 values, right? Just we discussed now 1, 2, 3 up to the 10 if we are having, then we are adding now 1 plus 2 plus 3. Similarly, we are adding the values of the V0 over 0 to 2 pi. And again divided by total count was 10, right? 10 numbers. So here we are having the total is 2 pi radian angle, okay? So it is like a integration means addition divided by 2 pi. Now similarly this can be written as V0 average. Therefore V0 average is equal to, yes, we can write it as 1 by 2 pi. Yes, in 0 to 2 pi the effective interval is from alpha to pi only, right? Because 0 to alpha V0 is 0, alpha to pi V0 is a non-zero, and pi to 2 pi V0 is again 0. So non-zero interval is only alpha to pi, right? Only alpha to pi. So therefore 1 by 2 pi integration from alpha to pi Yes, during alpha to pi, what is the V0 value? Yes, V0 value is same as that of the supply voltage. So it is a Vm into sine of omega t. Vm into sine of omega t into d omega t, right? So please try to understand. We are integrating it, means we are adding the instantaneous values and again divided by 2 pi, divided with 2 pi, right? So it is equal to Vm by 2 pi. Yes. What is the integration of sine of omega t? Minus cos of omega t. Limit alpha to pi. So after putting the limit, we can write it as Vm by 2 pi into 1 plus cos alpha. 1 plus cos alpha. This is a V0 average. Average value of output voltage is a Vm by 2 pi into 1 plus cos alpha, right? So here you can check alpha is the firing angle of the thyristor. If I change the alpha value, definitely my V0 average will change. Definitely my V0 average will change. Is this clear? Right? Next, so this is the V0 average. What about the I0 average? Average value of load current. Load is a purely resistive. Okay? So we can write I0 average is equal to V0 average divided by R. I0 average is equal to V0 average by R. Right? V0 average is this one. Okay? Either you can keep as it is or replace, you can replace your V0 average with this expression, right? Next, RMS value of output voltage, V0 RMS. V0 RMS. RMS stands for, come on. What is the, for, yes. The full form of this RMS. RMS stands for yes, RMS means what? It is a root mean square, right? RMS stands for root mean square. Yes, no, right. So here RMS stands for root mean square. What is that root mean square? Root is nothing but square root. M means mean, mean means average, and square, okay? Root mean square. Let me write here. RMS is nothing but root mean square. RMS stands for root square. So what it indicates? Root is nothing but square root. Square root. Mean is nothing but average. Mean means average, and square is nothing but simple square. It is a square. So what it indicates, root mean square means it is a square root of average of squared value, right? So here we need to first of all square that voltage. We need to find the average of that squared value and we need to put it into the square root. So it is a square root of average of squared value, that is nothing but root mean square. So how to find V0 RMS? Yes, we can write V0 RMS. V0 RMS is equal to square root of mean of squared value. So it is a 1 by 2 pi integration from alpha to pi V0 square d omega t and to the power 1 by 2. Please try to understand this expression. What this bracket indicates? Integration over alpha to pi V0 square means what? We are squaring the V0 value and divided by 2 pi. That is nothing but we are averaging it, na? Average of the squared value. Average of the squared value. And here it is a square root. So square root of mean of squared value. If you check the V0 average, in the V0 average, this square was not there. Yes or no? It was like only 1 by 2 pi alpha to pi V0 into d omega t. But in a RMS, we need to square it, we need to take the average and we need to put it into the square root. So square root of mean of squared value. So now we can simplify it, it is a straightforward. It is equal to 1 by 2 pi integration from alpha to pi Vm square into sin square of omega t into d omega t to the power 1 by 2, right, to the power 1 by 2. So now we can simplify it. Take the Vm square outside, this 2 pi outside. So V0 RMS, therefore V0 RMS is equal to Vm upon root 2 pi into integration over alpha to pi. This is sin square of omega t can be replaced with 1 minus cos of 2 omega t by 2. 1 minus cos of 2 omega t divided by 2 into d omega t na, to the power 1 by 2. Further, we can take this divided by 2 also outside. So it is equal to Vm upon 2 root pi into, yes, integration of 1 is omega t minus integration of cos of 2 omega t sin of 2 omega t divided by 2. Sin of 2 omega t divided by 2. Limit alpha to pi to the power 1 by 2. Right? Now straightforward calculation, we can write it is Vm upon 2 root pi into, it is like a pi minus alpha minus sin of, yes, 2 pi, sin 2 pi is 0, so plus sin of 2 alpha divided by 2 to the power 1 by 2. This is a V0 RMS. RMS. Okay, so V0 RMS is Vm by 2 root pi into pi minus alpha plus sin of 2 alpha by 2 to the power 1 by 2. I0 RMS is equal to V0 RMS divided by R. V0 RMS divided by R. Or it is equal to, we can write Vm upon 2R into root pi into bracket pi minus alpha plus sin of 2 alpha divided by 2 to the power 1 by 2. Right? This is the I0 RMS. Next, RMS value of load. Yes, same, we have already written I0 RMS, so no need to write here. Next, load power. Load is connected at the DC side and output side. So load power is nothing but average load power, that is a P0 average. P0 average. So how to find the P0 average? We know P0 is equal to V0 into I0 na? V0 into I0. So if you check the V0 waveform and the I0 waveform, you can check here. Yes. Yes. This is the V0 waveform, this is the I0 waveform. Right? So during 0 to alpha both are 0. So what is the P0? 0. Alpha to pi, V0 is non-zero, I0 is also non-zero. V0 is Vs, I0 is Vs by R. So P0 will be V0 into I0, it is a non-zero. And again pi to 2 pi, V0 is 0, I0 is also 0. So P0 will be 0 again, right? So P0 waveform, that is the load power waveform, will be having a non-zero value only during alpha to pi, only during alpha to pi. So let me write here, yes, P0 average, effective value is P0 average. Yes, it is equal to 1 by 2 pi integration from alpha to pi. P0 is non-zero only during alpha to pi. Just now we discussed, okay? It is equal to V0 into I0 into d omega t. We are finding the average value, right? Effective value at the DC is average. So it is equal to, we can write 1 by 2 pi into integration from alpha to pi. Now what is the V0? We know V0 is equal to I0 into R, yes or no, right? So we can write it is I0 into R into this is I0 into d omega t. So this can be written as 1 upon 2 pi into integration from alpha to pi. This is like a I0 square into R into d omega t. Further, this can be written as, we can take r outside, so it is a r into 1 by 2 pi. Please listen. Into 1 by 2 pi integration from alpha to pi I0 square into d omega t, right? I0 square into d omega t. Further, this can be written as, can we write it as P0 average? Therefore, P0 average, very interesting and very important, R into, we can write it as 1 by 2 pi integration from alpha to pi I0 square into d omega t to the power 1 by 2 and to the power or 2 square. Please check. The same expression I have written in this way. Why I have written in this way? Please listen. Yes, here what this term indicates? This term 1 by 2 pi integration over alpha to pi I0 square into d omega t to the power 1 by 2. It is like square root of mean of squared value, na? Means it indicates I0 RMS, right? And it's a square, means can we say that it is a I0 RMS square into this R? Yes or no? So this term is like your I0 RMS. This term is a I0 RMS. So therefore, P0 average, very important, is equal to I0 RMS square into R. Average value of load power in a purely resistive load is equal to RMS value of load current, its a square into R. Further, this can be written as, we know I0 RMS is V0 RMS divided by R, na? So further we can write P0 average. Also, P0 average is equal to V0 RMS square divided by R. And same this can be written as P0 average is equal to V0 RMS into I0 RMS. All these three are valid expressions of average output power, right? So please be careful. At the left hand side we are having the average power, but at the right hand side we are having the RMS values. So please be careful. If the load is purely resistive, your average power consumed by the resistor is always equals to RMS value square into R, or I0 RMS square into R, or V0 RMS into I0 RMS, or which is equal to V0 RMS square by R. Is this clear? Very important bit. It is not like that P0 average is equal to V0 average into I0 average. No, right? It is the left hand side average, but right hand side we are having the RMS values, right? Next. Yeah, conduction time of thyristor. You can recall the waveform. Conduction time means the time during which thyristor is in a on state. So what is the conduction angle of thyristor? First of all, let us check. Conduction angle of thyristor. Yes, let me, yes. 0 to alpha, whether thyristor is in a conduction mode or off state, thyristor is in a off state. Forward blocking, now we discussed. Alpha to pi, thyristor is in a conduction mode. Pi to 2 pi, thyristor is in a reverse blocking mode. So what is the conduction angle of a thyristor? Only this much angle, and this angle is pi minus alpha. This angle is pi minus alpha. So conduction angle is pi minus alpha. So conduction time is pi minus alpha divided by omega, na? Angle means omega t. So time is angle divided by omega. Okay. So let me write. Conduction angle of thyristor is pi minus alpha. Yes. Yeah. Conduction angle. Let me first write. Conduction angle thyristor is equal to pi minus alpha. So what is the conduction time? Therefore, conduction time is equal to pi minus alpha divided by omega. Pi minus alpha by omega. Right? Very important bit. PIV rating of thyristor, peak inverse voltage. So PIV means what? this PIV stands for peak inverse voltage. That is nothing but peak value of inverse voltage or reverse voltage. Reverse voltage, peak value of reverse voltage across thyristor. Okay, peak value of reverse voltage across thyristor, that is nothing but the PIV rating. So for that, please check the VT waveform, voltage across thyristor waveform. Yes, we have drawn. Yes, voltage across thyristor waveform. During 0 to alpha, VT is positive. So whether this is a forward voltage or reverse voltage, this is a forward voltage. We are interested in peak inverse voltage, that is a peak reverse voltage. Na? Alpha to pi, thyristor voltage is 0, thyristor is in a conduction mode. Pi to 2 pi, voltage across thyristor is a reverse voltage, na? Right? So what is the peak value of this reverse voltage? You can check. During pi to 2 pi, we are having VT is same as that of the supply voltage, it is negative, na? So if supply voltage peak value is Vmax, so definitely this value will be Vmax only. Are you getting the point? Peak value of reverse voltage across the thyristor is equal to Vm in this case. So it is a Vm. Peak inverse voltage across thyristor is equal to Vmax. Yes. Yeah. So PIV rating. They have asked the questions. PIV rating of thyristor is equal to Vmax. Is equal to Vmax. Be careful. It is not like a minus Vmax, because they may give the option like PIV rating of thyristor in a given circuit is, and suppose the option is like plus Vm, minus Vm, and remaining two are like Vm by 2 and Vm by 4. Don't get confused. PIV rating means peak inverse voltage. As in this term already the inverse word is there, na? Inverse means reverse. Okay, already there reverse term is there. So that's why while writing the PIV rating, we need to write the magnitude of that peak voltage, magnitude of the reverse peak voltage. Okay, that is the Vm only. We need to write the Vm only. Don't write here minus Vm. Definitely voltage is negative only, but this is the PIV rating, and in the term PIV, this I is the inverse voltage, na? Inverse term is already present. So that's why we need to write only the magnitude of the reverse voltage, right? Peak reverse voltage. So Vm. Circuit turn off time of thyristor. So how to find the circuit turn off time of thyristor? Please check. Very important. Yes. So for that again let us, yeah. Yeah. Circuit turn off time of thyristor. How to find the circuit turn off time of thyristor? Please listen it carefully. Very important bit. Okay. So first of all, let us find the instant or the angle at which thyristor current reaches the zero value. Circuit turn off time is having a relation with the commutation of Scr. Okay. So in order to find the circuit turn off time, first of all check the instant at which thyristor current becomes zero. So here we know at omega t is equal to pi, load current becomes zero. At omega t is equal to pi, load current is zero. Load current is equal to thyristor current, right? So if load current is zero, therefore your thyristor current is also equal to 0 ampere. After that, from this pi, the reverse voltage is maintained across thyristor till which instant? Till 2 pi. So circuit turn off time is nothing but time corresponding to the reverse voltage. Time corresponding to the reverse voltage, right? That is appearing across the SCR. That is nothing but the circuit turn off time. Okay, you will understand in detail circuit turn off time while discussing the commutation of SCR. But today's our topic is not the commutation of SCR. It is the rectifier. Okay. So TC, how to find the TC? First of all, we need to check the instant at which current flowing through SCR becomes zero, and after that till which instant the reverse voltage is maintained across the SCR. So at omega t is equal to pi, current flowing through SCR becomes zero, and after pi, you can check from this pi till 2 pi only the reverse voltage is maintained. After 2 pi, the voltage is positive, forward voltage is there, okay. We are interested only in a reverse voltage, na? So reverse voltage is present only during pi to 2 pi. So what is the circuit turn-off time? Circuit turn-off time, that is a Tc, is equal to 2 pi minus pi. So this angle is pi divided by omega, okay. So it is 2 pi minus pi by omega, that is pi by omega. So circuit turn-off time. Very important bit, circuit turn-off time. Yes. Circuit turn-off time. So Tc for thyristor. Tc for thyristor is equal to, Tc means circuit turn-off time, okay, is equal to 2 pi minus pi divided by omega, which is equal to pi by omega, which is equal to pi by omega. Is this clear? Right? So last point, input power factor, that is the supply power factor. Supply is AC, yes or no? And in AC we are having the power factor term, right? So input power factor. So how to find the input power factor, let us discuss. If you check the circuitry, in circuit we are having the single phase AC supply, that is a Vs. Second side we are having a load, and in between we are having only the ideal switch. We are having the ideal switch, that is the ideal SCR. As SCR is the ideal, so what are the power losses? Power losses are 0. So can we say that whatever the power supplied by the source is equal to the power absorbed by the load? Yes or no? Right? So source power is equal to load power. Source power is equal to load power. Please listen. Source power is equal to load power. Why we have written? Because in the circuit we are having only 3 elements. One is supply, second one is load, and third one is the ideal SCR. Ideal SCR power loss is 0. So here load power, power absorbed by the load is equal to power supplied by the source. So that's why I have written source power is equal to load power. But source is AC. So source is AC means source power is PAC, which is equal to load power. Load is a DC, na? So output is a DC. So it is a PDC. Now PAC means AC side power. What is the expression for power in the case of single phase circuit? We know it is a V into I into cos phi. So similarly here PAC means Vs into Is into cos phi s. Vs means source voltage. Is is source current. So this Vs and Is, these are RMS value of supply voltage and supply current. And this cos phi s is input power factor, that is a source power factor, which is equal to PDC. PDC means P0 average, which is equal to, we have written V0 RMS into I0 RMS. Yes or no? Right? So therefore cos phi s, that is the input power factor. It is also known as the source power factor. It is also known as the supply power factor. Okay, is equal to V0 RMS into I0 RMS divided by Vs into Is divided by Vs into Is. So cos phi s is equal to V0 RMS into I0 RMS divided by Vs into Is. Now, if you check the circuit operation, please check the circuit operation. For all the intervals means like 0 to alpha, alpha to pi, and pi to 2 pi. Is and I0, both values are same only. You can recall the circuit operation. During 0 to alpha, thyristor is in a forward blocking mode. Supply current, load current, both are 0. Alpha to pi, thyristor is in a conduction mode. Supply current is equal to load current. During pi to 2 pi, thyristor is in a reverse blocking mode. Right? So load current is equal to supply current is equal to 0. So for all intervals, source current and load current both are same. So can we say that RMS value of source current is equal to RMS value of load current? So that's why this will get cancel out. Please listen it carefully. Right? I am saying that supply current and load current values are same for all the intervals. Right? because RMS is equal to IS is nothing but IS RMS. This IS means IS RMS only. This IS means IS RMS. So it is equal to V0 RMS divided by Vs. And this Vs means what? Vs means RMS value of supply voltage. So this is the expression for input power factor. Very, very important. Is this clear? Right? So friends, this is about the single phase half wave controlled rectifier with a purely resistive load. Detailed analysis we have done here. Right? Okay. So, yes. If you are having any doubt, please ask. Already I think it is 9, means we are running out of time, okay, or exceeded. If you are having doubt, please you can post here. And one more thing, the same type of sessions are available on the ACE online platform, recorded videos, and I will be conducting during the live sessions also, okay. So very important subject, very interesting subject, application oriented subject, okay. This was only just like an introductory part here, right. So, and as long as your KPTCL is considered, the weightage is also very good, around 8 to 10 marks. So I think it is a very handsome weightage this subject is having. So you can enroll for the online classes as well as for the recorded videos also, right? If you are having any doubt, please ask. No doubts, then we can conclude here, okay? Thank you, thanks to all of you, and all the best.